All right, so in today's video, what we're going to look at is the vapor compression refrigeration cycle. Primarily because I'm going to stumble over saying that, I'm simply going to refer to it here on out as the refrigeration cycle. But I want you to be aware that there are more than just the vapor compression refrigeration cycles out there, namely the Rankine refrigeration cycle. Now, the reason we're choosing this cycle to look at as opposed to the Rankine refrigeration cycle is primarily to do with the amount of times that you're going to see the vapor compression refrigeration cycle in industry versus the Rankine refrigeration cycle. Many of you may never ever come across the Rankine refrigeration cycle, but almost all of you will encounter the vapor compression refrigeration cycle. And so it's a very good cycle to learn. It's a very good cycle to understand and to work through not only understanding the thermodynamics, but understanding the logic on how we're about to build this ideal system. And so I want to talk a little bit, before we get too deep into the weeds here on the cycle, I do want to talk about building this ideal system, which is what we're going to walk away from these first two videos with, really a set of assumptions that we've really made to make this best case scenario cycle. And you might be wondering, well, what's the purpose of this? Why are we doing this? Is it just so we can do some sort of academic calculations? Does it have any sort of bearing in industry? And the answer to that is yes, it does. It has a lot of bearing. But also the reason or the logic behind those assumptions, how are we building those assumptions, is very important. And you need to be well versed as a chemical engineer in building these types of assumptions to assess at a high level these different types of systems, whether they're going to work economically, whether they're going to work practically. And so as we work through this, I want you to pick up both the assumptions that we're building on the system that we're going to have here on the board, but also the methodology behind how we're going about this is also very important. So with that said, let's get into it. So let's break up this refrigeration system into its four major components. And the four major components of this refrigeration system are, and you can do these in any order because, as you'll see, the cycle is circular, so who's to say where we start at? So we got to pick a starting point, and I've picked the expansion valve. So the first major piece of equipment here is the expansion valve. And again, just because for ease of writing here, I'm just going to shorthand this as EV for expansion valve. The second major piece of equipment is the evaporator. And I'm going to label this shorthand Q, uppercase Q, lowercase c, give you a little bit of understanding of why I'm doing it this way. The expansion valve EV probably makes a little bit more common sense. But the Q, as you'll learn if you haven't learned already, is a common symbol for heat transfer. This evaporator is a heat exchanger. The C here is denoting that this is the heat exchanger on the cold side of this system or this cycle. This cycle is actually a cycle that has a cold side and a hot side. We'll learn a little bit more about that as we go to breaking down the system. The third major component of this system or of this cycle is the compressor. And I'm going to shorthand this WC. The W is just really kind of shorthand. Up to this point, you should have seen this, hopefully, in your thermodynamics course, where we kind of shorthand work as W. So we're looking at the work because the compressor is putting work in the system. And the C there is not for the cold side, it's for the compressor. You can come up with any shorthand you want. I'm just going to show you the one that I'm going to use throughout the videos. The fourth major component of this cycle is the condenser. And the condenser, like the evaporator, is a heat exchanger. So I'll use Q as part of its abbreviation and H as the other part, because the condenser is the exchanger on the hot side of this cycle. Now, what we're going to do, we've kind of listed out the 4 major components, and we're going to assemble those components here in something called a PFD for shorthand, or process flow diagram. It's really just going to be a big picture schematic to help us understand how these 4 major components are linked together, and how can we visualize them working together to bring about what the cycle is ultimately supposed to achieve. But before we get to drawing out that PFD, I want to talk a little bit about what the refrigeration cycle is actually achieving. And for many of you, you've had an AC unit, or you've had some sort of refrigeration that you're aware of, and you know that a refrigerator makes things cold, or it gets your food cold in the refrigerator. But I want you to think a little bit more along the lines of thermodynamics. Will that refrigerator get cold just naturally? Will your house get cold naturally? Let me ask it maybe in a better question. Let's say it's really hot outside one day, and you've got your AC running. If you were to turn your AC off, would you expect your house to continue to get colder? Or would it start getting hotter? Well, the answer is it would start getting hotter, right? That is because heat naturally is going to flow from a higher temperature medium to a lower temperature medium. And you might be laughing at this line of questioning as I'm going through it, but it begs the question, how is your AC able to take energy from a cold system and dispel it to the hot system outside? Because naturally, if we turn the AC off, that wouldn't happen. And that's fundamentally what you need to understand about this cycle. How is this cycle able to achieve that goal? How is it able to take energy from a colder temperature system and dispel that energy to a higher temperature system? Something in the natural world that we wouldn't see happening unless we put work into the system. That's the missing component there, right? If we were to turn the AC off, there would be no work being done to the system. There would be no work being done to your house. And so what's going to happen? Natural the thermodynamics is going to state that the hotter medium is going to now give up its energy to the colder medium, and they're going to eventually reach thermal equilibrium. So with that little thought experiment there, we've deduced now that this compressor, or maybe potentially something, is doing work with this cycle that's overcoming some of the quote-unquote laws of thermodynamics, right? We're not really overcoming those laws. The compressor is, if you want to think about it this way, is paying an entropy tax. You're having, in order to achieve this thing that goes against what we might call the laws of nature, we have to expel energy. We have to fight against entropy, so to speak. So just an important thought experiment as we go through this. I want you to understand, I'm always going to bring you back to understanding fundamentally what's going on in this system. That's your takeaway from this. If you don't understand what's going on in these systems, if you don't understand first principles, then you can do all the calculations that you want to. You can solve all of the home problems that you want to. But the amount of value that you're going to add to your team and industry once you get out into the real world will be minimal, because you don't know how to think through the problems. You don't know how these things actually work. Okay? So let's look at this system. And again, the system is circular, so we can really start with any point. But I'm just going to start as we listed them here. So I'm going to start with the expansion valve. And again, we're going to draw what in industry you would call this sort of a process flow diagram, or PFD. So if we start here with our expansion valve, and coming out of our expansion valve, the working process fluid will then travel to our evaporator, QC. Let me put my abbreviations here on the expansion valve. Now, as the working fluid travels out of the expansion valve to the evaporator, we're going to term this state right here state 1. We could call it state A, we could call it state 25. Doesn't matter. Again, we just want to label this to say, okay, when we say state 1, we're talking about the working fluid in between the expansion valve and the evaporator. So if your teacher labels this as something different, he or she is not wrong. So the next step in this sequence is after we come from the evaporator, the working fluid, the refrigerant, is going to come out of the evaporator and go into the compressor. Now between the evaporator and the compressor, we will call this state 2. The next step in the sequence is after the compressor, the fluid is compressed, discharged, and then makes its way into the condenser. Again, another exchanger. Between the compressor, after the fluid, the working fluid or the refrigerant is compressed, going into the condenser, we're going to call this state 3. Now, our condenser, the last step in our loop here, we're going to connect our loop. So the fluid, the working fluid, is going to come out of the condenser and go back to the expansion valve to go round and round. This state here between the condenser and the expansion valve, we're going to call state 4. All right, we haven't talked about what's happening here. We've just talked about the working fluid. We've talked about the sequence in which these major components are assembled. So you're kind of left again here with just a high-level diagram. We don't even know what's happening to the fluid in any one of these cases. So we're going to add that layer right now. So here in state 1, let's look at across the expansion valve between state 4 and state 1. Now I've called these states because it's ultimately what we're going to look at them as. So remember, a state has pressure, temperature, entropy, enthalpy, all these different state functions. So here, site 1 has pressure 1, it has temperature 1, we'll call, it has entropy, I wrote entropy 2 there, entropy 1, and enthalpy 1. And these are all referring to the state functions or the states at state 1. So what's this fluid here? How do we identify it? It's got a pressure, it's got a temperature, it's got an entropy, and it's got an enthalpy. Same thing with all these, but I'll go ahead and write out because we're going to evaluate between 4 and 1 what's happening to the fluid as it comes across the valve. So what happens here is, as it comes across this valve, what we have on step 4 over here is a higher pressure system, ultimately generated by this compressor. So the pressure over here at state 4 is higher than the pressure here at state 1. So we might write P4 is greater than P1. Now we can go through and further deduce some other things by making some assumptions. And so these will be our first kind of round of assumptions here. We're going to assume here that this at state 4, and this will make more sense once we come back around, but we're going to assume, for a starting point, state 4 is actually saturated liquid. Remember, saturated liquid is a liquid that is still in vapor-liquid equilibrium. It's not a subcooled liquid, but it's a liquid that's just hit the point of equilibrium. So it's got effectively one molecule of vapor that's flashed into the vapor space, but it's at its saturation point. Now, as the fluid comes from state 4 to state 1, what happens is this control valve actually acts as a restriction, meaning that just restating what we've already stated, meaning that the pressure here is going to be greater than the pressure here. And what winds up happening is because now we have a reduction in pressure, we also, because the liquid was already saturated, so we know that we're have vaporized some things here, because I'll give you that logic here. The pressure has gone down. So because we're at equilibrium, and we know that we're working, or we've assumed here, that we're working with a pure working fluid, a pure refrigerant, that constrains all the other state functions. So if the pressure goes down, the temperature also has to go down. And that's effectively what's happening as we come across this valve. We see a drastic drop in pressure depending upon how you size your system. So this pressure drop may be bigger in certain units and smaller in the other ones. It's going to be, again, dependent upon your design. But what winds up happening is now as we drop that pressure, we wind up getting a mixed system. So over here at state 1, we have vapor and we have liquid. And how much of each, again, is going to dictate it by how you designed your system, how it's operating. So now let's look at going from state 1 to state 2. What's happening here? Well, what's happening here is, as we come from state 1 to state 2, we go through this exchanger here, the evaporator. And ideally, if you designed your evaporator and your system correctly, what you would want to wind up with is saturated vapor here at state 2. So effectively what we're doing is we're sending this vapor plus liquid system. We don't know how much vapor or liquid at this point, but we could calculate that if we constrain the system some more. But we would want to design the system such that as we went through this exchanger, it sucked or it picked up enough heat from the surroundings in this exchanger to evaporate all this liquid. Again, we're looking at latent heat here. And again, so we're going to evaporate all this liquid. Everything now is going to be saturated vapor. Just like saturated liquid, this is still vapor-liquid equilibrium. And so we're still constrained here under vapor-liquid equilibrium. We'll also have a state here of pressure 2, temperature 2, entropy 2, and enthalpy 2. Again, all we've done here in this evaporator is basically pick up heat. Now, from going from state 2 to state 3, so if we go ahead and just write out all of our state functions we've been looking at. Now what happens is as we go from state 2 to state 3, we have this compressor. And all the compressor is doing is imparting work to this saturated vapor. So it's imparting work, increasing the pressure, and likely increasing some of the temperature, and what we wind up with is something we would call superheated vapor, which is really just a fancy way of saying it's vapor that's no longer in equilibrium with its liquid phase anymore. So it's not saturated, it's superheated. So we've increased the pressure, which means that one of the deductions from here is that because we've put work into the system, we've increased the pressure, we can know that P3 is going to be greater than P2. Now the last step here in our system is going from step 3 to step 4. And what we want to do ultimately is design this heat exchanger. Remember, I just kind of assumed here we're going to have saturated liquid, and we're getting back to how does this become saturated liquid. We would ultimately design this exchanger to take this vapor from superheated vapor to saturated vapor at the higher pressure and ultimately continue to cool it through that latent heat regime to saturated liquid. So again, this is just taking out heat or cooling it in this instance. So over here, if we were to divide our cycle in half, what we have over here is our cold side. Why do we call this our cold side? It's because the temperature of our working fluid over here is colder than the environment in which it's removing heat from. We call this the hot side because the working fluid here is hotter than the temperature in which it's expelling to. If you haven't got to this in thermodynamics, one of the major proponents of heat transfer is temperature difference. But heat is going to travel from a higher temperature to a lower temperature. That's why it's important over here, if this were your house and you want it to be at 74 degrees Fahrenheit, the temperature of your working fluid in the system has got to be 74 at best case, but it's more than likely you're going to have to be lower than that to achieve proper heat transfer. You'll get into that in a later class. But the point being is, at a minimum, this temperature over here on this cold side has got to be 74. It can't be hotter than that. On the hot side, if we're going to dispel that heat we just sucked from over here out to the environment, so we would need to know what the environment temperature is. In Louisiana, which is where we're filming these videos, I mean, it can run up to 105 degrees Fahrenheit some days. So your working fluid is going to need to be at least as hot as 105, but ideally it needs to be hotter than this. So the work that you're inputting from the compressor needs to bring this temperature of the condensing fluid up to 105 or greater for this cycle to work. So I hope we're at the conclusion of this first video. Just some takeaways. Remember, what did we look at? We really just built the basic structure for our refrigeration system. We looked at the 4 major components. Okay? Then we assembled those components within the refrigeration cycle itself to see how they work, and really kind of what's happening to the working fluid. How is it achieving what it's achieving? And how is it assembled in a certain way to achieve that desired result? And we also looked just at some deductions here from, okay, if this is working, if this is how this works, then we can infer that the pressure at 0.4 is higher than 0.1. We didn't assign a value to it quantitatively, but we can infer these things just from how the system should work. Similarly here, because we have a compressor compressing the gas, we know that P3 has to be higher than P2. How much? Again, that's going to be really based upon the design that you're looking at. But with that being said, we'll stop here for this video, and when we come back, what we're going to look at is how do we take this system that we looked at and build that ideal system, that benchmark, that perfect standard in which we can go out and evaluate maybe different cases with. Thank you. Okay, so what we looked at in the last video, let's just go through a recap. Again, we looked at the 4 major components. We assembled those 4 major components, built a PFD, and really kind of looked at what's happening in a big picture with this system. Now what I want to go do is let's build out our assumptions to make the base case. And really this base case is going to be, maybe a better term for it is the ideal case or the perfect case. Because what we're going to try and do is, we're going to try to make some good assumptions to try and figure out the most perfect cycle possible, okay? We're never going to be able to achieve this cycle, but we want to have this bench line to say, this is what perfect looks like, so we can measure our other cycles by that to say, how close to quote-unquote perfection are they? Are they an ideal cycle? Are they a perfect cycle? Or are they 85% of an ideal cycle? Okay? So that's one reason that we would do this. But the second reason is really the more, I guess, practical reason. So let's say before we were designing this process, and we're actually going to work through an example here in one of the later subsequent videos. Well, let's say we were looking at a refrigeration cycle to upgrade in our unit, because this new upgraded refrigeration cycle, maybe it had a bigger compressor, maybe it had a bigger condenser, but it was a more beefed up unit. It gave us more chilling capacity, it gave us more heat removal on this cold side. Well, in order to build that, in order to get that higher cooling capacity, for say, let's pretend for instance that we needed this higher cooling capacity to make the reactor run faster. Okay? How much energy now are we going to have to input on this compressor? Well, we could go through the whole detailed design every intricate detail of the compressor, the piping, the heat exchanger, the valve, the other heat exchanger, and we could go through that whole detailed process and waste everybody's time to come up and figure out that this isn't going to work. We're not going to save money because all the added production that we made in the reactor is going to be offset by the increased compressor cost. So it would be very nice to have a quick way to analyze this cycle, maybe against an ideal case, to say, listen, we can't get any better than this, right? So if anything, it's going to cost more energy to get us this cold. The point being is, I can do a quick calculation for this ideal cycle we're about to make and say, if it doesn't work for the ideal cycle, it's not going to work for any of them. So I don't need to waste my time detailing out all the intricacies of this cycle for something I could do in 5 minutes and go back to the business guys or go back to whoever proposed this idea and say, look, we got to come back to the drawing board because this isn't going to work. We're not going to make money doing this, okay? So let's go through some assumptions that we're going to need to make in order to build our ideal cycle. And we're really going to walk away with 5 major assumptions. Most of the assumptions are going to be around the major pieces of equipment. So let's look at these. So I'm going to put up here ideal cycle assumptions. The first one's going to be around the expansion valve. And I'm abbreviating this EV. And we're going to assume that the expansion valve is irreversible. It's frictionless. And it's adiabatic. Now, from classical thermodynamics, you should have an understanding of what irreversibility is, but let's just talk about it at a high level. Remember, we're going from pressure 4 to pressure 1 in a finite step, based on classical thermodynamics. That makes this an irreversible process, because remember, reversible processes increase or decrease by infinitesimally small amounts. So, although in the real world there is no such thing as an irreversible process, a reversible process, remember the reversibility is this ideal, much like we're about to make an ideal cycle, this ideal concept of perfection. But we can approach this reversibility much closer than just a valve. We could put here a turbine, which would then be a Rankine cycle. We won't talk about why we won't put a turbine there, but know that you can, but it doesn't really give all that much payback. But in any case, because it happens, it's an irreversible step here. The second assumption revolves around our evaporator. And we're going to assume that is isobaric. So what does that mean? That basically means that the pressure between state 1 and state 2 is the same. So we're going to assume that P1 equals P2. Because we're at equilibrium, what does that also mean? It also means that the temperature is the same. So T1 equals T2. The third assumption that we're going to make is around the compressor. And we're going to assume that the compressor is isentropic. Now you may be saying, There's no such thing as an isentropic compressor, Josh. You're right, there isn't. But again, what are we trying to build in this ideal model? Trying to build the best case. So in our best case, we're going to assume that this compressor is actually reversible, meaning that the entropy at state 3 is equal to the entropy at state 2 because the compressor is not imparting any entropy. It's isentropic. The fourth assumption that we will make is that the condenser is isobaric, just like the evaporator, right? So what does that mean? That means also that P3 is equal to P4. These pressures are equal. Very key to note. Remember how we said pressure here is equal to pressure there, and also the temperature here is equal to the temperature there. Remember how I said that's because they're still in equilibrium. We still have saturated vapor, and we have a vapor-liquid mixture. Not the case here. We have a superheated vapor going to a saturated liquid. So the temperature here does not necessarily equal the temperature here. The last assumption that we're going to make here in constructing our ideal cycle is the piping. We're going to assume that the piping is frictionless, meaning that it's not going to lose any energy as it flows through the piping. Once you get to fluid dynamics, you're going to realize, hey, that's impossible. I know. Again, we're trying to build the best case. So we're going to eliminate the friction here, even though in practicality, that's not going to happen. So you see that we're building this perfect standard that's not really achievable. So if you walk away from an evaluation that the perfect standard is not going to make you money, nothing else is going to work, okay? It's important. I'm drilling that home, but I want you to understand the importance there because a lot of people miss that. The other assumption that's baked in here into this piping is that it's adiabatic. And all we're getting at on the adiabatic portion is that there's no heat transfer happening on these pipes. The only heat transfer that's happening is in the exchangers, okay? And so with these assumptions, we've just constrained the system to a point that we can go through and solve for how much work it takes to get this working fluid. We'd have to constrain the system further and say what type of refrigerant are we going to use. And we'd also have to constrain the system and say what's our hot temperature medium and what's our cold temperature medium. What do we want T1 to be and what do we want T4 to be, okay? But once we do that with our ideal assumptions, we can go through and solve to figure out how much work the compressor actually has to impart in the system, which is the important part of this cycle because that's what we're going to pay for to run is this compressor, okay? So real quick, the next video we're going to look at the diagrams. I'll explain those a little bit more, but I want to recap what we just went over. Ideal cycle assumptions. Remember, we said that the expansion valve is irreversible. We can make it close to reversible if we were to put a turbine, but remember we have a finite step change. It's frictionless, adiabatic, so it's not causing friction loss here, although once you get to fluid dynamics, you're going to say, that's not right. And then also we're assuming that it's adiabatic, so it's not going to exchange energy with the surroundings. Again, all the piping, frictionless, adiabatic. Both of the exchangers, what we're assuming here, and again, once you look into heat transfer and fluid dynamics, you also say, Josh, it's kind of a bad assumption because what's happening here between state 1 and state 2 and state 3 and state 4? Notice you have a phase change. Phase changes in exchangers normally have a decent pressure drop. You're right. But what's our purpose? Our purpose here is to give ourselves an ideal baseline. So it's going to work, okay? We're going to walk away with an ideal baseline because the only thing that a pressure drop here is going to do is cause the compressor to work more because it has more restriction, okay? We assume that the compressor is isentropic. In real life, that will not be the case, but for our ideal model, it's good. Because the only thing that's going to happen is now in the real world, it's not going to be isentropic. It's going to be inputting work into other things other than pumping the fluid. So once we start working some examples here, a lot of these assumptions, you'll see how these assumptions help us constrain the system. In the next video, what we're going to look at are TS, or temperature entropy diagrams, and pressure enthalpy diagrams. Thank you. All right, so this is going to be the second to last video, at least in the kind of introduction to this refrigeration cycle. So far, we kind of started with the 4 major components, assembled those, got a decent understanding of kind of what's happening to the working fluid as it travels through this sequence of events, this sequence of components that we call the refrigeration cycle. And then in the last video, we looked at the ideal cycle and how we develop assumptions to make this perfect benchmark that we know going into it is not going to be achievable, but also understanding it gives us a level of analysis, or a perfect standard to kind of shoot for when we evaluate different technologies, when we evaluate different scenarios. We can kind of know, hey, will the best case work? And if the best case doesn't work, we know right away this isn't going to work at all, okay? So what we want to look at in this video are, we're going to call diagrams. And we're going to look at relevant diagrams that when you get out into industry, and even now you'll probably work through some practice problems, but these diagrams are going to help you understand the system that you're designing. And there's really 2 parts to these diagrams. The first part is going to be, call it the working fluid, or the refrigerant. So the refrigerant phase diagrams. I'm going to make a little bit more sense of what I'm talking about here in a second. And the second one we're going to look at is our actual system diagram. And the system diagram is actually going to be overlaid on the phase diagrams. So one of the things in developing a system here, one of the constraints that you as the engineer, or whoever designed it before, or whatever you're left with, or whatever has been designed in your plant, maybe a better way to put it, is the type of refrigerant that's either going to be used or that is used will be a constraint. And what you will have is, you will have 2 different types of plots that you're going to be looking at. These will be TS diagrams, or TS plots, temperature versus enthalpy. Excuse me, not enthalpy, entropy. I'm getting confused here. So just rehash on this video. Remember, TS, remember S is the shorthand notation for entropy, not enthalpy. Temperature versus entropy. And pressure versus enthalpy. So let's look at a refrigerant. It'll be the same refrigerant that we actually use in one of the practice problems. We'll look at a refrigerant. I'm just going to kind of segregate here. So let me use a different color marker so it's, and I'm kind of going all over the board here. Let's kind of segregate some of our stuff so we know what belongs to what. So let's say we're going to construct a TS diagram, which is temperature on the y-axis and entropy on the x-axis, or S. And we're going to look at, we're going to look at this for refrigerant R134A. That's the refrigerant we're going to use in our practice example. We chose R134A because it's a common refrigerant, at least at the timing that this video was filmed, of the refrigerant that's actually used in automobiles. So the AC, or the refrigeration system within your automobile, for the most part, is likely going to be an R134A system. So if we were to look up R134A saturated vapor liquid equilibrium data, you can look at this on NIST. We'll actually have an example once we get to the practice problem of how to construct these diagrams using the data, but we can go pull that data from a multitude of different resources, but NIST, the governmental website, actually has this that you can go pull for free. And if we were to go plot temperature versus entropy for saturated vapor to liquid systems, we should get a phase diagram that looks something like this. Again, I'm just freehanding this, but this should be the general nature of the curve, some sort of upside down parabola. Now, over here on the outside hump of the curve, this is going to be our subcooled liquid. On this side, we're going to have vapor. And in between here, this is our vapor to liquid equilibrium region. Now, just a quick back of the envelope check, we can say that, hey, I'm not lying to you. Is this truly, should this be the liquid or should this be the vapor side? How would you double check me to make sure that, yeah, that sounds reasonable? Well, if we look at our curve here, what's on the x-axis? Entropy. Should a liquid have a higher or lower entropy than the vapor? Should have a lower one. Okay, so that's a bit of evidence to say that I did this right. Same thing over here. A vapor should have a higher entropy than the liquid. Now, a similar plot that will be useful is the pressure enthalpy plot. And if you were to do this again we'll take R134A, but for most refrigerants you should have this type of graph. But if we were to go look up this, take pressure and enthalpy data for the saturated vapor and liquid, we should walk away with some sort of graph that looks something of this nature. Still kind of an upside down parabola, but it's got this elongated lobe shape here that's kind of unique of the pressure enthalpy curve. And again, we will have the liquid on this side, the vapor on this side, and vapor liquid equilibrium here in the middle section of this upside down parabolic shape. Again, you can check me here. Same kind of logic that we used over here, that's used over here. Should a liquid have a lower or higher enthalpy than the vapor? Should have a lower. Vapor should have a higher. Kind of a double check there. So what we've just constructed here, at least qualitatively, are the refrigerant phase diagrams. We've taken temperature enthalpy plots, pressure enthalpy plots, and we've constructed the phase diagrams, ideally for our R134A system. Now next what we want to do is we want to take the system diagram. So our refrigeration loop here, we want to plot that on both of these graphs, okay? I know we don't have actual values here, but if you did, it would be the same procedure that you're going to use. It's going to be a little bit less intuitive since we don't have numbers, but I'm going to show you how to logic through this. Okay? Let's start at point 4 for our temperature entropy diagram. It's a saturated liquid, so we know that it has to exist somewhere on this curve right here, somewhere on the left-hand side of this curve. Where, we don't know because we don't have a quantitative number for our temperature. But let's just pick a point. Let's just say that this, we'll call this point 4. Okay? Now, as we go across this expansion valve, what happens? Well, we know that the temperature is going to go down. We also know that the valve is irreversible, so the entropy is going to go up. So we don't know exactly the shape of this curve, but it should look something maybe of that nature. Maybe it's a straight line. We don't know, okay? We're just taking a qualitative approach here. But we know that the entropy is going to increase and the temperature is going to decrease. Let's just say it stops right there. So this will be point 1. Now from state 1 to state 2, what's happening? We're removing latent heat. Remember, when you're removing latent heat, what's happening? The pressure is staying the same because we assume that it's isobaric. Pressure 1 equals pressure 2. But also because it's latent heat, only latent heat that we're removing, the temperature is staying the same. So what should happen is we should take a horizontal path from point 1 all the way to point 2. And where does point 2 exist? Remember, it's saturated vapor. So we're going to come a horizontal line all the way until we intersect this line. If I can draw a horizontal line, we'll try. If this looks off when you're looking at it, no, it should be a horizontal line. If it's not a horizontal line, you'll have to forgive me. This is point 2. Now what happens from point 2 to point 3? Well, we increase the pressure. But one of the constraints that we had from our ideal cycle was that the entropy is constant. And what are we graphing here? Temperature and entropy. So we're going to have a vertical line somewhere. Where does it end? We don't exactly know. Okay? Well, we do know, but I haven't got to that point. We have a vertical line coming here. So let's just draw a vertical line. We're not sure right now. We haven't deduced enough information here to say we can know where it stops. However, what assumption did we make from going from 3 to 4 across this exchanger in our ideal model? We assumed something. Remember, we assumed that it's isobaric, meaning that the pressure here at state 3 is equal to the pressure here at state 4. Okay? Although this is a temperature entropy diagram, what you'll commonly see on these temperature entropy diagrams are isobars or constant pressure lines. So and I'm not going to draw all of them, but I'll show you kind of the behavior they would exhibit. I'm going to draw it through point 4. It's going to stay constant. It's going to stay constant. Coming across here, hits the vapor line, comes up. It'll have some sort of characteristic like that. Again, this is our isobar. So the pressure here is going to be pressure X, but we'll call it pressure 4. P equals to P4. So this is the constant pressure line on this graph. So what's going to happen is we're going to increase the pressure coming across this compressor to the pressure that we desire based upon the design of our compressor. But we're going to stop at point 3, or pressure 3, which is also equal to pressure 4. So as we come isentropically, so straight vertical line, we're going to intersect with this pressure line here. Again, we'll have other ones that will be coming down on this graph. If you look at one, a lot of these graphs are very cluttered, so you have to know what you're looking at, and that's why understanding the general behavior of the lines helps, so you can know which line is what. Or we'd come up here until we find the pressure that equals our pressure 4. And this will be our state 3. I'm just going to erase this pressure bar so you can, I just want you to see the nature of the actual system curve. So here we've gone up, oh man, I'm not good at drawing. We come up here isentropically, so entropy is constant. And now what we're going to do is from state 3 to state 4, we're cooling this. We're going from superheated vapor to saturated liquid. And we're going to do that. How are we going to do that? Remember, isobarically. So we're going to follow this isobar down to the saturated vapor line right here, and then all the way across to state 4. So now what we've done, we've built our refrigerant phase diagram for our TS diagram, and we've also now superimposed the system diagram on that. I'll leave that exercise for doing that here for you, but it's the same principle as when we went through for the TS diagram, okay? Notice how we walk through that. We assumed, right, start at step 4. We know step 4 is going to be somewhere on this line. Pick a point, okay? Everything about this so-called practical exam that I've given you is qualitative in nature. You don't need any information as far as the quantity of the pressure or the quantity of the enthalpy, okay? All right, when we come back, we'll be finishing up with kind of big picture, the refrigeration cycle, and we're going to look at doing an energy balance on the different components. After that, we'll look at a practical exercise and conclude with some field walkthroughs and just looking at equipment field verifications, troubleshooting, etc. Thank you. All right, so this will be the last of what we'll call the introduction to refrigeration. We'll go through a brief walkthrough of what we've talked about so far. Again, 4 major components. Drew our PFD, have a decent understanding of the assembly of these 4 components, what's happening to the working fluid. We built our ideal cycle, understanding the importance and also the limitations of these assumptions in building this ideal cycle. We looked at diagrams, different plots. We looked at the phase diagrams we talked about R134A, but really these phase plots aren't for R134A. They're more so just generic phase plots and kind of giving you the resemblance of what it should look like. Same thing for pressure enthalpy. And we also went through and constructed a system diagram on the TS diagram for kind of qualitatively what this refrigeration cycle should look like. We also left the pressure enthalpy diagram for you to do on your own. The last portion that we want to get into is looking at the energy balance associated with this system. Now, traditionally in chemical engineering, we would also talk about a mass balance. However, given that this is a closed system, we're assuming no mass enters or leaves the cycle. So really the only importance here is the energy balance. And I'm going to use a blue marker since the board has become quite messy, so you can clearly distinguish between the energy balance information and all the information we've already gone over. Before we start drawing our system boundaries here, I want to draw out or write out the equation for the energy balance equation. I'm going to write it out and then I'll explain what each piece is. So here's our generic energy balance equation. Over here what we have is the accumulation of energy per unit time. In most, at least lower level classes in chemical engineering, you always assume steady state. So what winds up happening to this term a lot of times is we assume that it's zero. If you get into process controls, once you get into that level of coursework, this assumption here really doesn't become valid anymore. Your process control dynamic models are really focused on the time variable. So in any event, for now, we'll assume that this is a zero. Right here, what we're looking at is the change, this D right here, that's change, so differential change in enthalpy between two different points. What we're looking at right here, so this is the internal energy change here of the system. This is the kinetic energy change. Notice the m1/2 v squared. This right here is the potential energy change from the gravitational potential energy. This term right here is accounting for heat exchange or energy loss via an exchanger, dq. And the change in work is either work done by the system or work done to the system. For instance, the compressor is an example of something that's doing work to the system. Whereas if we had a turbine up here, which we don't, we have a valve, but if this was a Rankine cycle, refrigeration cycle that is, we would have work being done by the system to the surrounding. So if we do some other simplifications here, at least for our examples, we're really not going to consider the kinetic energy change of the system. We're also, at least not for our base case here, going to really consider the gravitational difference, but depending upon your system and your plant, if you have a refrigeration unit that goes very high up, maybe to an overhead condenser or something that's on a tall platform, this could potentially become not negligible anymore. So when we reduce down our equation, the equations that we're going to be using here to evaluate this will look something like this. So we're really going to be only dealing with changes in internal energy, heat transfer, and work input to the system. And that's what we have here, right? We have work being put input, and we have heat being transferred. So let's draw a system boundary at 4 different, and basically label out 4 different systems here around each major piece of equipment. We'll call this system boundary 1. Call this system boundary 2. Call this system boundary 3. Call this system boundary 4. Now what we're going to do is start to develop equations for the energy balance for system 1, system 2, system 3, and system 4. However, because I'm running out of room here, I'm going to erase all of our diagram stuff here. I'm also going to erase some of the state information right here. I want to erase this just to give me some more room while I'm going through these energy balances. So let's look at system 1 and write an energy balance around that. So system number 1. And what's happening? We have fluid coming in here, fluid coming out here. No mass is lost, right? The mass coming in is the same as the mass coming out. There's no work being exchanged, so the valve isn't There's no work happening because remember we assumed that it's frictionless, some of our ideal assumptions. And there's no heat exchange. So what do we have here? We go back to our original equation that we derived over there. 0 equals the mass N times the change in internal energy or enthalpy. Remember, we're assuming here there's no change in mass, closed system, minus the lost or absorbed heat, minus the work input. Both of these are 0. Therefore, what we have is, and if we go from state 4 to state 1, and we evaluate this differential here, what we wind up having is M H4 minus H1. That's our system 1 balance. Now I'm going to erase this so I can keep my room, but we'll have our final result here under system 1. And I didn't reduce this far enough. So we have our mass, which can be factored out. If we divide by mass on both sides, what we're left with is 0 equals H4 minus H1, which means that H4 equals H1, which means that here, H1, that's supposed to be H4, sorry. H4 is equal to H1. We deduce that from the energy balance. So here, our most simplified term here is H4 equals H1. Now let's look at system 2. Again, we can start with our energy balance that we reduced down over there, that 0 equals M, change in enthalpy, minus the change in heat transferred, minus the change in work done to or by the system. So if we come over here and look at what's happening, we have mass coming in the system, mass coming out. We know that it's the same because we assumed a closed system. But what's happening? Right? We have an evaporator, so what's going on right here? The system is doing what? It's gaining energy. Energy is being added to the system. Is there any work being done here? There's no work being done to the system or by the system. Therefore, Q is not 0 anymore, like in system 1, but work, however, is 0. So if we reduce this down, what we have is dQ is equal to M dH. So what's that saying? It's saying that all the internal energy, the change in energy for the system, is directly related to the amount of work, or excuse me, the amount of heat exchange in the exchanger. Does that make sense? What would change? What's changing between step 1 and step 2 that would change the energy? It should be directly proportional to the amount of energy that's absorbed. So we can just kind of logically deduce that we're on the right track here. And if we further kind of refine this, what we have is, and we integrate this, what we'll wind up with is dQ is equal to M dH. Right? And so the energy exchange there, which this dQ is QC, is going to be equal to M H2 minus H1. And notice I just said dQ is QC because that's how we've been labeling this QC, this heat exchange right here. Okay? So again, I'm going to erase this, I'm going to bring this up here so we can go through the last two. Just leaving it there so you can still see it. All right. Now let's look at system 3. So what are we going to do here? I'm going to start with our reduced energy balance over there. Now let's use this and evaluate system 3. So what's happening? We've got our working fluid coming in and coming out. Mass is conserved. What's happening in the system? We have work being done to the system by the compressor. So our work term is non-zero anymore. What about heat? Is there any heat being added to the system? No, there's no heat exchange here. At least we've assumed that. In practical, there may be some minor heat exchange, but in our ideal model, again, our ideal model, this is 0. So how do we reduce this now? We have the change in work is directly correlated to the change in energy of enthalpy of the system. That should make sense. The only thing happening here between state 2 and state 3 is work is being done to the system, so the change in energy of the system should be directly correlated to the change in work. If we integrate this, we'll wind up with work, change in work, or your work input here is equal to the mass of the system times the enthalpy change. And again, this can be, we can denote that as WC if we'd like to. All right, I'll erase this. Let me write this as WC. Work with the compressor. Okay. The last system that we have to look at is system 4. And I'll write it right here. Tell you what, just for uniformity, I'll write system 4 right here. We'll do all the proofs right here. Okay. So we'll start with our reduced energy balance over there. 0 equals m dH minus dq minus dw. And let's look at what is happening between state 3 and state 4 in our ideal system. The only thing that's happening is we're adding energy, we're taking away energy from the system. So we know that we have heat exchange going on, but there's no work being done to the system or by the system. This term is 0. If we rearrange the equation, we have dq is equal to m dH. If we integrate that, we have dq is equal to m dH. If we further kind of evaluate that or put in our known terms here, we have QH is equal to m H3 minus, H4 minus H3. It's always final state minus initial state, and we're evaluating it going from this state 3 to state 4 in the workflow of the system. Transcribe that over here. Okay. So there you have it. Our energy balance around the system and around all the subsystems. Now it's important, just like in building the ideal model, don't just memorize the assumptions. I want you to understand how we got there, why we got there, because that's going to be important for you to be able to shape your mind, shape your thought process, to be able to do this on your own in other areas. I want you to take that same approach to this energy balance. How did we assume away this accumulation term? How did we assume away this term right here? The kinetic energy term. How did we assume away this term? The potential energy term. How are we just doing that? Are we just making that up to make our lives easier? Or is there some sort of valid logic that we can do that and still walk away with a good result? You need to understand that. You need to train your mind to begin to understand these things. Okay? So again, that concludes the kind of introduction to the refrigeration cycle. I hope this helps. At the next video, we will go into a detailed example of applying everything we've learned so far to an actual scenario that I've worked out in the plant. Thank you.